In this video, we'll be learning how to calculate support reactions and drawing of bending moment and shear force diagrams. So this is a simply supported beam with 2 point loads acting at point C and point D. So the total span of the beam is 9 meters. So question says we should calculate the support reactions. So let's start with that one first. So this is a hinge support or a pin support. So a hinge or a pin support has two support reactions. So it gives a vertical reaction and a horizontal reaction. So we'll call the vertical reaction VA because it is acting at A, and we'll call the horizontal reaction HA. Okay. Then at point B, this is a ruler. Okay, a ruler support. And a ruler support gives only one reaction. Okay, so we'll call this one VB. So we'll be using the three equilibrium equations to calculate the support reactions because the support reactions will help us to draw the bending moment and the shear force diagrams. So you can take moment about any one of the supports. So let's choose support A. So sum of moments about A should be equal to 0, or in other words, sigma MA should be equal to 0. So the 80 kilonewton force will cause a clockwise moment because you're taking moment about A. So let's take clockwise to be positive. So 80 kilonewton is causing a clockwise moment. So it's going to be 80 times the perpendicular distance to where I'm taking the moment, which is 3. Then plus because 60 kilonewton will also cause a clockwise moment. So it's going to be 60 times the perpendicular distance from where this force is acting to where I'm taking the moment, and that's 6 meters. Okay, this vertical reaction will cause an anti-clockwise moment. So that's going to be minus. So VB multiplying the perpendicular distance from where VB is acting to where I'm taking the moment, and that's 9, be equal to 0. The horizontal reaction will not cause any moment because it is acting at where you're taking the moment. So there will be no perpendicular distance, so it will be 0. So now let's calculate for VB. Let's move VB to this side. So this times this will give us 240 plus 360 is equal to 9 VB. So when we sum this, the 600 is equal to 9 VB. And we'll divide through by 9. So VB will give us 66.67 kilonewton. And that's the vertical reaction VB. So you have to make use of another equilibrium equation, and that's the sum of vertical forces. So you can call it sigma Fy is equal to 0, or the sum of vertical forces to be 0. So let's take forces moving up to be positive. So VA is a force moving up, it's a vertical force. Because it's moving up, it's going to be positive VA. And VB is also moving up, so it's going to be plus VB. 80 kilonewton is a vertical force which is coming down, so it's going to be minus 80. 60 is also coming down, so minus 60. Everything here is equal to 0. So these are the vertical forces. So VA plus VB should give us, when we move these two to the other side of the equation, we should get 80 plus 60. We already know VB, that's 66.67. So let's substitute. So VA is equal to this plus this is going to give me 140 minus, so the VB is moving to this side, which is 66.67 kilonewton. So VA is equal to 73.33 kilonewton. So that's the vertical reaction VA. So we've calculated for VA and VB. Now I left with the horizontal reaction, which is HA. So to calculate HA, we have to sum forces in the horizontal direction, or we have to sum horizontal forces. So sum of horizontal forces should be equal to 0. So HA is the only horizontal force. So let's take forces moving at the right side to be positive. So this is positive. So because it's moving to the right, it's HA, positive HA. That's the only horizontal force. So we equate it to 0. So we have found VA, VB, and HA. So shear force is the sum of the vertical forces acting at a particular point. So when I section the beam, or when I cut the beam at point A, I have to sum the vertical forces at point A to get the shear force at point A. So when you make a cut at A, you choose to take either your left or your right. But this trick helps me in calculating for shear force, and I'd like to share it here. So for the shear force, the calculation for the shear force at each point, you have to calculate two of the shear forces. What do I mean? So shear force at A, we'll calculate for what we call shear force at A prime and shear force at E. For shear force at C, we'll calculate for shear force at C prime and shear force at C. For shear force at D, shear force at D prime and shear force at D. So let's start with the first one. So shear force is the sum of the vertical forces. So shear force at A is equal to 0. So shear force will always start from 0 and it will end at 0. So shear force at A prime is 0. Then that means that I have to calculate for shear force at A. Shear force at A will be equal to, so shear force at A will be equal to the previous value, which is 0. Okay, then you factor in the vertical force, which is acting at point A. So we have VA, which is acting at point A. So VA is a vertical force moving in the upward direction, and we stated earlier that forces moving in the upward direction is positive. So that means 0 plus VA will give me the shear force at A. So we know VA to be 73.33. So when we sum this, we will get 73.33 kilonewton. So that's the shear force at A. So we've calculated for shear force at A prime and shear force at A. Now move on to the shear force at C. But for the shear force at C, we'll calculate for shear force at C prime. So shear force at C prime will be the previous value, which is 73.33 kilonewton, just like that. So with that one, you will not factor in the vertical force, which is acting at point C. So after calculating for shear force at C prime, and calculate for shear force at C, and shear force at C will be 73.33. So the previous force, which is 73.33, then we'll factor in the vertical force, which is acting at point C. So it's a vertical force and it's moving down. So we'll consider it to be negative. So it's going to be minus 80. So minus 80. And this is going to give us negative 6.33 kilonewton. So that's the shear force at C. So using that same idea, then we'll move on to shear force at D. So we have to calculate for two of them. So shear force at D prime. The shear force at D prime will be equal to the previous one, which is negative 6.67 kilonewton. Then you move on to shear force at D. So shear force at D, you pick the previous one, which is negative 6.67. Then you factor in the vertical force acting at D, and that is 60. But because it is coming down, it is negative, so it will be minus 60. And that's going to give us negative 66.67 kilonewton. So there's the shear force at D. And then now you come to the shear force at B. So calculate for 2. So shear force at B prime will be equal to previous one, which is negative 66.67 kilonewton. Then shear force at B will be equal to the previous one, which is negative 66.67. And we factor in the vertical force acting at point B. So the vertical force acting at point B is VB, and it's moving in the upward direction. But we've already calculated for VB, and that's the 66.67. Because it's moving up, it is positive. So it's going to be plus 66.67. And this will give us 0. Good. So like I said, you start from 0, then you end at 0 when it comes to calculations for the shear force. So when you are drawing the shear force diagram, to start from 0 and it will end at 0. So after this calculation, then we'll draw the shear force diagram. So shear force diagram. So we'll draw something like this. So this point is A, and this point is, so looking at this point is C, and we'll come to point D, and we'll come to point B. So you just have to plot the points. So your shear force at A is 0. So it started from 0. At A prime was 0. At A was 73.33. So that means I'll still be at A. Then I'll plot 73.33 kilonewton. So still at E. Then now I'll move to the shear force at C prime, 73.33. So at C, so it will be on the same line as this. So 73.33 kilonewton. And I just have to connect the two, a straight line. Now the shear force at C, negative 6.67. So the top is positive and down is negative. So negative 6.67 will be somewhere here. So negative 6.67. So I'll bring it down, still acting at point C, kilonewton. Then shear force at D prime, negative 6.67. So D, negative 6.67 will be on the same line as this. So negative 6.67 kilonewton connects the points. Then shear force at D is negative 66.67, and still at D, negative 66.67 kilonewton. So I'll have to move down to this point. Then shear force at B prime, negative 66.67, here, negative 66.67 kilonewton, and connect these two. Then lastly, shear force at B, I have to come back to 0. So 0 is on the line, then 0. So this part is positive, okay, this part is negative. So this is the shear force diagram. Onto the bending moments diagram. So we have to do the calculations for the bending moments at the various points. So the bending moments, so you have to calculate for bending moments at A, B, C, and D. So unlike the shear force, where we calculated for two values at a particular point, for the bending moment, we only calculate one. So I have to make a cut, okay, at point A. So I'll make a cut at point A, and I'll choose to take either my left or my right. Where you make the cut is where you take the moment. So because I made the cut at point A, I'll take moment about point A. And I'm taking my left side. So because I'm taking my left, I'll take the moment to my left. Okay. So moving to the left, this is the moment moving to the left, and I'll call it BMA. So this means the bending moment at A. So it's moving in the anti-clockwise direction. So it's going to be negative BMA. But because I took my left, there's nothing there. This horizontal force will not cause a moment. So it will be equal to 0. So when I divide through by the negative, I'll get the bending moment at A to be 0. So use the same idea for C, D, and B. So bending moment at C, I'll make a cut at C, then I'll take the moment. So I'll pick my left. When I take my left, I'll take moment to my left, and I'll call it the bending moment at C. So it's moving in the anti-clockwise direction. So I'll say negative BMC. Negative BMC. So I've made a cut, so this part of the beam is not there. So negative BMC. Then this VA will cause a clockwise moment. So plus, because clockwise it will be positive, plus 3VA. So this vertical force times the distance to where I'm taking the moment. Because I made the cut here, I'm taking the moment here. Everything is equal to 0. Because this is the only force that will cause a moment. The horizontal force will not cause a moment. I already know the value of VA. So let's move BMC to this side. So BMC will end up becoming positive. It will be equal to 3VA. But I know VA to be 73.33. So this will give me 219.99 kilonewton meter because it's a moment. Then you use the same idea and calculate for the bending moment at D. So bending moment at D. Okay, so if I take my left, or this force will cause a moment, this force will cause a moment. So I can choose to take my right. So because I'm taking my right, I'll take my moment to my right, and I'll call it BMD, bending moment at D. So the bending moment at D, moving the clockwise direction, so it's positive. Then this is the only force that will cause a moment. So it's going to be minus, it will cause an anti-clockwise moment, so minus 3VB is equal to 0. That's all. So you can choose to take your left and solve, you still arrive at the same answer. So BMD is equal to 3 multiplying VB. So I've moved it to the other side. VB was 66.67. And this will give me 200.01 kilonewton meter. So that's the bending moment at point D. So now the bending moment at point B. So I'll make a cut at B and I'll take the moment to my right because I want to pick my right. And that's the easiest. If I take the moment to my left, that means this will cause a moment, this one will cause a moment, and this will cause a moment. And I want to escape the long work, so I'm picking this side. So bending moment at B is moving in the clockwise direction, so it's positive. So positive BMB is equal to 0 because there's no other force here. I've made a cut, so there's no force here again. So bending moment at B is 0. So now let's draw the bending moment diagram. So the bending moment diagram. So point A, so point C, point D, and point B. So point A, bending moment at A was 0. Okay, so 0 here. The bending moment at C gave us 219.99. So you can plot it at point C, 219.99 kilonewton meter. Then I'll connect the two. So this is at point C. And the bending moment at point D was 200.01. So 200.01 will be somewhere here. So 200.01 kilonewton meter. Now join the 2 points. So let's say it's here. Okay. The bending moment at B finally to 0. So I just have to extend from this point to 0. So this is the bending moment diagram, and it's all positive. Thank you for watching this video.